Hello everyone. Today we will perform the synthesis of Frambinone. As you guys all know, the Frambinone is a known chemical and frequently used in the perfume and the cosmetic because of its smell. And that's the structure of the Frambinone. We can see we have a hydroxy group here and also a ketone groups here. And if we do the ritual synthesis as you learned in the lecture, so we will go backwards. And that's the structure, the backbone. Of course, we cannot break the benzene ring here, so we will cut here. So the first thing we can think of is we can add a double bond here. And if we do the hydrogenation, we will reduce the double bonds to the single bond. So we will add the double bond first. And because we add a double bond, we can easily split the double bonds through the outer condensation from these two components. We have that one is the acetone, and that one is the aldehyde. And with the outer condensation, the base here will take off the proton here, and then we will have the enolate. The enolate will attack the CO double bonds, the carbon here, and after the reduction, and we will have the double bond here. And once we have the CC double bond, we will do the hydrogenation with the palladium, and we will have our final product, which is the Frambinone. And let's go over what we're going to do. So for the first step, we will do the outer condensation. I will go over the mechanism very quick here, and for all the details, you can check our lab note, and they can tell you if you have two aldehyde, or if you have two ketones, or if you have the mixture, what kind of possibilities you have. So here we have one aldehyde and one ketone. So to perform the outer condensation, you need to have a beta hydrogen in one of the components. And here, of course, we have the aldehyde here. There's no beta carbon, so there's no way for the sodium hydroxide, the hydroxy group, to pull off the proton from here. So here is the only options. We have the proton here, we have the OH, will attack the proton, and that one will go here. Then we will have the anion here, and that one is the enolate structure. You can draw the enolate structure through the resonance structure. And the double bond can go here, that one can go here. We will have a resonance structure. We'll call that the enolate. And with the anion here, we can use that to attack the CO double bond. We'll kick the electron to here, and through one-step reduction, and it's the acid here, we will have, through the one-step elimination, we will have double bonds, unsaturated ketone. That will be the intermediate of the first steps, and that will be the brief experimental things we will do here. So we will add all three components, the starting material 1 and the acetone and the sodium hydroxide, into the flask and let it sit for 4 to 7 days. And we will have them here. We will have the solids, the solidified solid here. And as we show here, we will have a lot of our reactive sodium hydroxide here. So we need to use acid to neutralize it. Need to add acid to neutralize it. And they will go to the organic phase. Two phase, they will go to the organic phase. Then we will combine all the organic phase to another flask. And remember here, we will use ether to do the extraction. And ether easily absorbs water, so we will need to dry it, add some drying agent. To dry it. And finally, once we have the product, we need to use hot water to recrystallize it. And we need to add hot water to recrystallize it. And they will dissolve in the hot water, and we will bring it down. That is let it recrystallize in a week, we will have the solid, it precipitates into the Raman flux, and we will save it for the next period of the lab, which is the hydrogenation. The hydrogenation, as we show here, we have the product here, which is we synthesize from the first period of the labs, and all we need to do, we will need to add the hydrogen gas on these two carbons, like here and here, and we will have the target molecule, which is a Frambinone. However, it's not easy to react or introduce a hydrogen gas into the system, because that one is dangerous and it's not an easy access hydrogen source. So we use the ammonia. We use the ammonium formate as the substitute hydrogen source to replace the hydrogen. Here we have the ammonium formate here, and with the palladium catalyst, that will break the bond here and spontaneously give you the hydrogen gas and sodium hydroxide, sodium dioxide, and also the ammonia gas. Three components will sorry.
Do you want to start over with the hydrogen portion?
Yeah, maybe here.
Okay.
Okay, so then let's jump to the second part. Once we have the product, the recrystallized product from the first period of the lab, we will perform the second part, which is hydrogenation. And we can see, you can see we have the CC double bond, and we already have the main skeletons of the target molecule. And what we need to do, we need to perform the hydrogenation from the hydrogen gas and add one hydrogen for each carbon, and then we'll have the target molecule. But however, the hydrogen gas is explosive and also is dangerous to perform in the lab. Then we will find an alternative hydrogen source which is safe to use in the lab, which is the ammonia formate. And with the ammonia formate here and with the palladium catalyst, that will produce three gas at the same time, and one of them is a hydrogen gas. So that will be used as a hydrogen source, and that's how we're going to do it. We will have the recrystallized the intermediate from the first step, and then the sodium formate. And in the book, there's a stoichiometry table you need to fill. So make sure you write down all the exact mass you actually want, and also write down the concentration. And for the reaction, you will prefer a larger flask because we will have a lot of gas produced in the system. So that will easily accumulate the pressure. So if you use the small flask, that could be dangerous. So say if you have like 10 ml of the solvent, you will prefer at least 3 or 4 times larger the Raman flask, say like the 50 ml of Raman flask at least. And once you have all the components into the Raman flask, we will go and heat it up and let the reaction go. And once we have the reduced products, like the target molecule here, we need to separate it with the palladium and the carbon. So the palladium and carbon is a solid. So we need to separate our products from with a solid there. There are 2 ways to do the filtration. An easy way or conventional way to do it is just we do the vacuum filtration. The palladium carbon will stick on the filter paper and our product can just go through it. However, we only have a very small amount of the product there. If we use a large bridge funnel, a lot of like the palladium catalyst will just stick on the filter paper, which is not very efficient. So we prefer use a small tiny filter this time. So we will just load all the material into a syringe and let them go through and push them go through the filter membrane, and the palladium and the carbon will stick on the the filter membrane here, and our product will go through the filter or go into the rumble flask. And that one is just an easier version of the vacuum filtration, but that one is more expensive. So if we are performing the large scale, we still prefer the huge funnel. And if we just very small amounts, and then we will prefer the filter, the membrane. And once we have all the product here, and we will do the final vacuum, the extraction, and all the product will go to the organic phase and do the rollback and concentrate it out. We will have our final product. And here are all the data we need in this lab. For the first period of the lab, we will need to perform one TLC plate. And for the TLC plate, you are required to do at least 3 spots. One is the study material, which will be here. That will be the study material. And M means the mixture of the study material and the intermediate. And the intermediate will be here, the product in the first period of the lab. And you need to perform the 3 spots and elute the TLC plate. And also, you will need to write down the yields, like how much crystal you got, and also the appearance of your product. Say if it is a color is crystal or the needle like crystal, you want to write them down. And for the second period of the lab, you will still need to do one more TLC plate, a study material, and the intermediate. It's the same from here. And also the final product, 3 spots, and let them go. And you can clearly see they are different material. They have a different RF value. And also, once you have the product here, you want to write down the yields. And also, because the Frambinone here, it will have a strong smell, you will also want to describe the smell of the chemicals. So also write down the appearance, like the smells or how it looks like. If it is oil, then just write down the oil here. And also, we will perform the NMR and also the melting point if you don't have enough material. So that's all for this lab, the synthesis of the Frambinone. Here's the synthesis of the Frambinone. The first step is the aldehyde condensation. Here's the pre-weighted 4-hydroxyl benzoaldehyde and also the acetone. And we will let it fully dissolved, let it fully dissolved. And we will add 2 ml of the 6 mol sodium hydroxide to trigger the reaction. And you can see the color starting become the orange-ish, and we will let it sit for 4 to 7 days to let it fully react. And after the 4 to 7 days, we will work up the reaction. After like a week waiting, we can find the product starting become like the orange-ish. So what we are planning to do, we will extract the product through these chemicals here. And the first thing we will have to do is we will neutralize the unreacted or the remaining sodium hydroxide here. What we're going to do, we will use 3 mol hydrochloric acid to neutralize it. And besides neutralize the sodium hydroxide there, the one more thing is because we have the OH on the benzene ring, that one is also acidic. So if we don't neutralize it, that will also react with the sodium hydroxide. So that will likely bring our product into the aqueous phase. So the first step here, we will add 5 ml of 3 mol hydrochloric acid. Around 5 ml into the flask. And let it stir for 10 minutes to fully neutralize the sodium hydroxide. Perfect, so we'll just let it stir for 10 minutes. After stirring for 10 minutes, we have the neutralized product here. We have the neutralized product here, and we will do the extraction. So we will pour it into the centrifugal funnel and wash that with the ether, and we will pour the ether into the separator funnel, and to the extraction, we'll combine all the organic phase together. Then through the drying agents, and rotovap, we will have our final product, and we will perform the recrystallization into the water. After the recrystallizing from the hot water, we observed some white crystal precipitate out from the cold water, and we will use those. We will do the vacuum filtration to collect the solid and use it for the second step, the hydrogenation. We have already pre-weighed the intermediate ammonia formates and also the palladium carbon, and disperse them into the methanol and ether into the solution into here, and we will let it reflux for 20 minutes. After the reflux, we will let it naturally cool down to room temperature, and also let it sit in the ice bath for at least 5 minutes. Here is the flux I took from the ice bath, and we will let it go through the filter. As I mentioned, this is an easy version of the vacuum filtration. So we will just pour the solution into the syringe. And slowly push it through, let it go through the syringe, and we will collect the aliquot in the rumble closing. And we can see the membrane effectively block the palladium carbon, and we can clearly see the clear solution we got after the filtration. And if you observed any of the palladium carbon go through the membrane filter, you will have to switch to another filter and do it one more time. And with organic phase here, we will do one more extract with the ether and combine organic solution, and rotovap to concentrate it down. That will be our final product.